Let's start. Henry, we're going to talk today about friction. Friction, we think, is due to the interlocking of molecular hills and valleys between a surface and an object on the surface. Although the surfaces may appear smooth, on an atomic scale, if you zoom in, they are not. And so we think as objects try and move relative to each other, those microscopic hills, those molecular hills and valleys kind of grip onto each other. I'm saying we think because as far as I know, we still haven't conclusively proved that that's what's causing it because we don't have the technology to zoom in that small. That's our theory. We think it's right, but until we actually can zoom in and confirm it, I'll keep saying we think. But it makes sense. The key idea, what you want to underline, is that friction resists sliding. Some people will say, well, friction resists motion. Actually, no. Sometimes it resists motion, but sometimes it can create motion. And this was a concept that I really had to try and push at you last year, especially for cars. So example one says, draw the direction of friction in each case. For a sliding block, these graphics were typed in Word 1995 for Mac, and they're starting to show their age. It looks like this block is hovering like an air hockey puck or a hovercraft. It's not. That's supposed to be actually touching. Just let me point that out. Okay. Kevin M., if we're sliding this to the right, which way is friction going to be pointing if it resists sliding? Yeah, friction would be pointing in that direction. Ooh, what about for a car speeding up? Well, when you step on the gas, the tires apply a force backwards against the road. Forces come in, and so the road applies a force forwards on the tires and thus the car. What is the force that the road applies forwards? It's why you can't drive on ice. Yeah, and this was a really tricky one to try and convince you of that for a car speeding up, friction is what makes a car speed up. I think I told you I was at a physics conference once. Don't write this down because this is bad physics. And I had a teacher write a free body diagram for a car. They did that, which was good. They did that, which was good. And then they had F engine and friction. I said, that can't be right because that would mean the smaller friction was, the icier the road, the better you drive. They hadn't thought about that, but right? If you get rid of friction completely, you'll drive better. Is that the case? Do you drive better on ice? No. And so I had to politely explain to this person. Now, I felt they were not a physics specialist. They were teaching it out of subject and they were just doing the best they could, but I had to correct that. Ooh, Bishop, what about when you hit the brakes? When you step on the brakes, the tires actually try and apply a force forwards against the road. Forces come in. And so, which way is friction pointing when you step on the brakes? Backwards. How do I know that's correct? Because can you stop on ice? No. And if you're ever dealing with a situation and you're not sure which way friction is pointing, Sophia, a good thought puzzle is put it on ice, and if it doesn't work anymore, yeah, the force that you're dealing with was friction. And usually we're pretty good at imagining that because you've walked on ice. So we talked a little bit last year about the direction that friction acts, the opposite direction of sliding. Then we said, how do you calculate it? We said it depends on two things. The first thing it depends on is the type of surfaces that are in contact with each other. Ice is slippery, sandpaper is not. We have a number that describes how sticky or slippery objects are in relation to each other. It's called the coefficient of friction. Declan, what's the first word there? Starts with a C? When I write 3x squared, which of those numbers is the coefficient? Yeah, a coefficient is something that goes in the front of. That's why the coefficient of friction goes in the front of. It's a dimensionless quantity. What symbol do we use for the coefficient of friction? We use the Greek letter mu. I'm sure I made the joke last year. What's mu? I don't know. What's mu with you was the dumb joke that I kept saying last year. A higher mu means a higher coefficient of friction. That would be grippier. A lower mu means a lower coefficient of friction. That would be slipperier. So steel on ice has a coefficient of friction of about 0.01. If you're skating and you give yourself a push and you line your skates up parallel, the thing that's slowing you down, it's almost completely air resistance. Oh, how many of you have watched speed skaters in the Olympics or on TV? What force did I just say is the one that's mostly slowing you down? I've just explained their pose and those suits that they wear and the helmets that they wear. Yeah, they're trying to reduce air resistance because coasting is good. Okay? Rubber on concrete has a coefficient of friction of about 0.75. That's why we use tires on our cars for traction. I should point out, though, this one varies an awful lot depending on temperature. I'm guessing all of you have noticed, say, when you're riding your bike on a really hot day when it's like 33 or 34 degrees on the pavement, your tires stick better. And you may have noticed on a really cold day, if you've ever gone bike riding when it's minus 15, when we have one of those Arctic blasts, when it's a clear, cold day, you don't have quite as much grip. So there's some variation there. Just saying. The second thing that friction depends on is the forces pushing the surfaces together. We said last year heavier objects are tougher to slide, lighter objects are easier to slide, but I need to explain why if I lift up it gets easier, or if I push down it gets harder. What is the force that pushes surfaces together? What do we call that? Friction is what times what? Mu times the? Yeah, we said it's much better. A much better thing to use in our equation is the normal force, Fn. And in fact, in the box way down here, we can write our equation. The force of friction is mu times the normal force. I don't know the normal force. I'll have to do a free body diagram. Last year, I don't know the normal force. Often, oh, but look. I know another force the same size as the normal force. It ended up being mg. It will, for the next couple of lessons while I'm reviewing Physics 11, often be mg. But then, honestly, for the remainder of this unit, it'll never be mg. We're going to get more complicated. So, Luke, don't ever memorize friction is mu mg. It's mu times the normal force. In fact, if anybody said that last year, that was probably one of the few times when I brought out the Nerf dart gun and pretended to try and point it at them and threaten them. Like, I've never said friction is mu mg, except in saying that I'll never say that. Ooh, example 2. Consider the block below, which is being pulled by student number 1. Let's say it's Justin. You know what? Instead of a block, Justin, let's make it the wooden benches at the back of the gym, the ones that you have to slide around and move out of the way for sometimes for basketball drills and such. Okay. You're pushing it along a rough surface, along the gym floor, and you're pushing it at a constant speed. That's important. Suddenly, student number 2, let's say it's Keaton, comes along and he pushes down on the block. He sits on the block, on the bench. Because of course he would, while you were pushing it along. He would come along and sit on it. If Justin maintains the same force as before, we want to ask what happens to the weight of the bench, the normal force, the force of friction, and then what happens to the motion. But before we can answer that, you know what this is a good job for? Yeah, we're going to do a free body diagram. Now, I did a free body diagram here. So, Justin, let's do this one here. Justin, what are the forces acting on the bench? Get the obvious one. And I think it's the same as before. Are we sinking into the ground like quicksand? Are we flying here like Superman? So there's going to be a normal force pointing up. Bigger, smaller, or the same size as mg? Why bigger? Yeah, you got the meathead Keaton. Yeah, you're actually, your response should have just been elbow Keaton when I said why bigger. Him. Yeah. I'm going to exaggerate it so it's stupid obvious. The applied force hasn't changed, but there's still going to be friction. Am I going to draw friction bigger, smaller, or the same size as this arrow? Why? Friction is what times what? What force just got bigger? In fact, I think we've answered the questions. Now, in drawing it, I'll do that. And now I can answer the questions. So first of all, did the mg of the bench itself change? Did the weight of the bench itself change? So part A says what happened to the weight of the bench? Same. Ah, but Justin, what happened to the normal force? Why? An extra force down. What if Keaton had been nice? Yeah, I know it's unlikely. What if Keaton had been nice and lifted up a little bit? What would happen to the normal force? Yeah, okay. But we're going to say the normal force increased. Well, if the normal force increased, what happened to friction? What if, again, what if Keaton had been nice for a change? I know, we're in our dream world, and he had decided to lift up a little bit. What would happen to the force of friction? Okay. Then D says, what's going to happen to the motion of the bench? So here, the forces were balanced. Are the forces balanced? Which way is the bench going to accelerate? Be obvious. So how will that manifest itself if you're moving to the right and you're accelerating left? What's going to happen to your... Yeah, someone said it. Slowing down and come to a stop. Again, let's go back to our dream world. What if Keaton had been nice and lifted up? The bench wouldn't slow down. The bench would accelerate. Oh, and maybe this is too stupid obvious. What if you and Keaton had applied enough force to lift the bench up completely? If it's in the air, what's the normal force exactly as a number if there's no surface? What would the force of friction be exactly then as a number? Yeah, you're all at the stage in the next 10 years of your life, you're probably going to move. You're probably going to move 3 or 4 times. You're going to change locations, whether you're moving into a dorm at university, when you're moving out on your own, and you're going to be helping your friends move. The way it works, you're going to find in your 20s, for pizza, you help move your friend, you buy them pizza, they help you move. And you're going to figure out the tricks of the trade of moving. First of all, if you can carry it, that's the best way to do, no friction. But then there's going to be a couple of things that are so stinking heavy, you're going to have to slide it, but you're going to figure out if I can lift up while sliding, I can reduce friction. Because especially if you're renting, I don't want to scratch the floor, my friend's going to lose their damage deposit, or I'll lose my damage deposit. Or you buy, the other thing you can do, instead of lifting up, they sell in hardware stores these little coasters. They look like coffee coasters. They look like almost an upside down cap of a mushroom, where if you get 4 of them, you can put the 4 couch legs in them and they slide way easier. There, what are they changing in the friction equation? What do those ones change in the friction equation? They change the coefficient of friction, and they seem like a great idea until you realize that if you leave them on your couch, every time you sit down in the couch, it moves back a couple of inches, and it moves, and eventually it's going to end up against the wall. So a lot of people initially, I'll put them underneath all my furniture and all my stuff. It'll move really, really easy. You don't always want it to move easy, but they're a handy thing. You can impress your friends when you're moving them if you show up with 4 of those in your jacket pocket and say, "Hey, let's use this to slide the couch around." They'll think you're pretty cool. Just saying. So we can change friction by changing the normal force or by changing the coefficient of friction, and all of you will do a fair bit of moving in your next 10 years. It's how life works. It says explain your answer using principles of physics. There's my explanation. I did a good free body diagram. In fact, that's the best explanation. No words, good physics. Example 3 says this. A student gives an old shopping cart a big push on a flat, rough surface. Which of the following is the best force diagram for the cart after the student has released it? So the cart, it looks like it's moving to the right, so we gave it a push to the right, but then we let go of it while it's rolling. Which of these is the best free body diagram? You know what? We're going to vote. Sorry for those of you on headphones on YouTube. That little thump was probably crazy loud on your ears. I apologize. I won't do that again. We're going to vote. How high you hold your hand up is how sure you are of the answer. So imagining a cart that's been pushed on a rough surface after we've let it go. Who says, I think diagram A is the best free body diagram? I got 1. I got 2. I got 3. I got 4. I got 5. I got 6. I got 7. Keaton? No? Okay, hang on. Let's try that again. Who says diagram A? Okay. Let me phrase that differently. Why must this be the correct answer? Let's see if we can figure it out. How would this object, D, how would that be accelerating? Which way must that accelerate? That would be speeding up. When you let go of a shopping cart, does it spontaneously start to speed up on its own? So I know that's right. That's wrong. Okay? Unless what? Yeah, an outside force, but we don't have that in the free body diagram. How would this one behave when you let it go? Would not stop. It couldn't possibly stop. For it to stop, there would have to be something slowing it down. That's going to behave like outer space. That's going to keep going in a straight line at a steady speed. Why? Because all of the forces are, I'm looking for a word that starts with letter B. Yeah. And then this one is interesting. I can't quite tell whether these two are equal. If they're equal, then it's the same situation as C. It's going to behave like outer space. Or Declan, it almost looks like this arrow is a bit longer, then this one would speed up. But that can't be right either. What must be the correct answer? It's got to be A. Which one of Newton's laws did I just use when I was talking about accelerating in the unbalanced force or not accelerating because forces are balanced? Which one of Newton's laws? Newton's first, Newton's second, or Newton's third? Now, I said you didn't need to memorize it, and so if you don't know which one it is, you would write only A has an unbalanced force slowing it down, and I would totally accept that. But which one is, huh? So I'm going to write Newton's first, since somebody said Newton's first, as my using principles of physics right to explain. But otherwise, if you didn't know that, you would say only A has an unbalanced force slowing cart down. Okay? I think I gave you this same puzzle last year, and we had about a 25% split on all four of them. A lot of people liked D because they were confusing velocity with acceleration. Well, it's moving forward, Mr. Dueck, so there must be an arrow pointing forward. And I'll say it again. You're going to hear me say this a bunch, Kevin. Newton's laws tell us nothing about velocity. They tell us about acceleration. Example 5. Says for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know, the first thing I'm going to do actually is I'm going to just draw a line down the middle of the page so I can do each of these separately. Luke, what does A want me to do? I can't do that because you know what this is a good job for? You know how I should start this out first? What might this be a good job for? So let's you and I do the free body diagrams, plural. Let's look at the first one. What are the forces acting on this 10 kilogram mass? Go systematically, get the obvious one. Is it sinking into the ground like quicksand? There's going to be a normal force. Is the normal force going to be bigger, smaller, or the same size as mg in this first diagram? I totally agree. What was the name that we gave to the 20 newtons, the mystery force coming from off the page, if we were just going to give it a label? What did we tend to call that one? F what? F applied. So I'm just going to put an arrow F applied since they, or an equal sign F applied since they gave me the arrow. Which force am I missing? How do I know there's friction? What's me with you? Yeah, not much. That's a very small coefficient of friction. If you were walking on a surface with that, it wouldn't be ice, but you'd have to be carefully keeping your balance. You know what? That's about mud on a slippery trail. If you've ever stepped every once in a while and had your foot slip on a slippery trail, it's about that. So it's not quite as slippery as ice, but you would have to pay attention to your walking if you were on a surface like that. You would not just be casually power walking and having a conversation. That's just nerd trivia. You don't need to know that, but I always like to try and give you a context. So friction, and Luke, I'm going to make the assumption that friction is smaller than F applied. If I'm wrong, I'll find out because when I solve for acceleration, what might acceleration be if I pick the wrong winner? Negative. There's a pretty obvious, I messed up. Hey, second diagram, what are the forces acting on it? Get the obvious one. What about the normal force here? I'm going to tell you it's not the same size because there's an extra vertical force, that 15. Is the normal force bigger or smaller than mg? Yes. I'm going to make it stupid obvious again, Luke, so that I don't miss that. And then we have F applied. And I'm still going to make the assumption that friction is smaller than F applied. I'll find out if I'm wrong when I crunch the numbers. Okay. Gershon, A says write a vertical force equation. Let's do the first one. Are we sinking into the ground like quicksand? Are we flying into like Superman? What that means is everything up has to equal everything. More specific, what is the only force pointing up in the first diagram? Has to equal what is the only force pointing down? You know what? My vertical force equation is Fn equals mg. What about this diagram here? What's my vertical force equation? Same rule. What's everything up? What's everything's down? You said 15 plus mg. I wrote mg plus 15. Same diff. Yeah. Okay. That's good. B says find the force of friction. Sophia, friction is what times what? So I'm going to write friction equals mu times the normal force. And then I often say, I don't know the normal. Wait a minute. Apparently, in A, the normal force is equal to mg, is it not? So let's just say it equals mu mg. I can crunch the numbers here. It's going to be what's mu? I don't know what's mu with you. 0.12 times 10 times 9.8. I can do this in my head. It's going to be 98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 10.8. It's going to be 11.76, I think, Sophia. Double check me. 11.76? Oh, Sophia's still writing. Is it? Yeah. And I'm going to keep all the extra sig figs because I have a feeling I'm going to be using this. So I'm going to write 11.76 and then I'll round to 3 sig figs newtons. Oh, Sophia, in the second diagram in B, what does B want me to find? The force of friction. Friction is what times what? Mu times the. And I was again going to say, I don't know the normal. Wait a minute. Apparently, the normal force is mg plus 15. I'm going to do that in brackets. I'm going to go friction equals mu, and then in brackets, mg plus 15. I could crunch that ahead of time, but you've clued in. If I can do it in one step, I'm going to do it in one step. It's going to be, what's mu? I don't know. What's mu with you? 0.125 times 9.8 plus 15. Oh, I think I can do that one in my head, too. 5 times 9.8 is 40. Yeah. 5 times 9. Not 5, Mr. Dueck. It's 10. Why did I write 5? It's 10 times 9.8. I'm so sorry. Made a mistake. 10 times 9.8 is 98 plus 50. That's 113. 113 times 0.12 is going to be 11.3 plus 2.26. 13.56, Sophia? Or no? Yeah. And then I'll say 13.6 newtons. Jacob, what does C want me to do? Who's winning in the first diagram, probably? Who's losing in the first diagram, probably? Equals what? Who's winning in the first diagram, probably? You know what? I think it's the same equation. Now, does that mean I'm going to get the same answer? No, because the values are different. Raghav, what does D want me to find? How would I get the A by itself in both of these equations? By? Yeah, divide by M. I named that after somebody last year, I think, in each class. I can't remember who it was. We called it someone's theorem. But yeah, divide by, I'm going to get A equals F applied minus friction divided by M. A equals F applied minus friction divided by M. A is going to be 20 minus 11.76 divided by 10. That I can easily do in my head. 8.24? 0.824? I think. Double check me. And A is going to be, if I'm wrong, give me a holler. I might be wrong. 13.56 divided by 10. That I'm dividing by 10. I better be able to divide by 10 in my head. 0.644. Am I right for both of them or am I wrong? Is A right? 20 take away 11 would be 9. Take away 0.7 would be 8.3. Take away 0.06 would be, yep, 8.24 divided by 10. 0.8. Yes? Woohoo! Both of them, not a very big acceleration. The applied force, who did the free body diagram? Luke, you and I did the free body diagram. We guessed right that the applied force was the winner. Barely. How would we know if we guessed wrong? Get a negative answer, but it's a fairly easy fix. In fact, later on, when we get to really complicated ones in this unit, I'm usually going to guess that F applied is winning, and if I guess wrong, I'll just do a quick correction rather than retype everything. There can be friction on an object even when it's at rest, because the hills and valleys will lock up when we apply even a small force to an object. In fact, you may have noticed there's actually two types of μ's. There's what's called static coefficient of friction and kinetic coefficient of friction. If you ever tried to slide something really heavy, you have to push harder to get it to start sliding than you do to keep it sliding. The force of friction on an object at rest is called static friction because static means not moving or changing. Ooh, here's a thought puzzle. Suppose we pull on a desk with a force of 2 newtons and the desk does not move. Which of the following is true? We're going to vote. A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. So if I pull on a desk with 2 newtons and it does not move, who says, well, duh, it's because static friction is bigger than 2 newtons. Obviously, it's A. 1, 2, 3, 4, 5, 6, 7, 8. Oh, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I got 14. I got Achi half up and then half down and then half up and then half down. I got 14 going once, 14 going, 14 it is. Why are they all wrong? You know what this is a good job for, Jacob? There's the desk. What are the forces acting on it? Get the obvious one. And I think the normal force, same size as gravity. Now, I'm applying a force, 2 newtons, yes? What 3 words did I underline? If it's not moving, what's its acceleration exactly as a number? Which means forces must be, I'm looking for a word that starts with, so how big must the force in this direction be exactly? Now, it can be bigger. What if I pull with 3 newtons and it doesn't move? How big is friction exactly? What if I pull with 10 newtons and it doesn't move? How big is friction exactly? So static friction is this weird force. It will match you until you go harder than it can match. So let's suppose the maximum static friction can be is 10 newtons. If I pull with 9.99 newtons, how big is friction? 9.99. What if I pull with 10.000000001? Now it will accelerate. Oh, and now a different coefficient of friction kicks in. You'll find friction just got smaller than that maximum of 10. Oh, it says explain your answer using principles of physics. I'm pretty sure I used Newton's first again. I said, if it's not accelerating, Evan, the forces must be balanced. Can't believe 14 of you went for that one. My last class, no one went for that one. I couldn't even let it go on. I got to fix this. Does that make sense? And those 14 of you that picked that, you should be feeling a little sheepish. I've taught you better and you understood this better. So don't always go with your first gut instinct. If you haven't figured it out from the tricycle demonstration, if you haven't figured it out from this is a good job, hey, a free body diagram in your head is a good tool to go with sometimes. Static friction is thus a force that varies from 0 when we're not pushing on the object up to some maximum value, and once you go bigger than that maximum value, the object will accelerate. We calculate static friction. Friction is mu times the normal force, but we use a static coefficient of friction, which is usually a little larger than the kinetic coefficient of friction, which is the one that we use when we're moving. I'm not going to distinguish between the two. I'm talking about this purely because a few years ago I had a student raise their hand, Leo, and they said, how come, Mr. Dueck, when I push on something, once it starts to move, I don't have to push as hard to keep it moving? So I'm answering that question. If you get a coefficient of friction in a question, Sophia, you can assume that it will work both for static and for kinetic. I'm not going to distinguish, except for this one question right here, example 7. It says a 5 kilogram object sits on a surface, and you can see, Liam, I've given you two coefficients of friction. The static one, a little bigger, the kinetic one. A says find the force required to move the object. That's going to be static friction. It's going to be mu static times the normal force. That's how hard we have to pull to get this object to accelerate in the first place. Liam, you know what this might be a good job for? I'm going to do it up in the right here. I got some room. What are the forces? Let's imagine. What are the forces acting on this mystery object? Get the obvious one. Normal force. There's going to be some kind of an applied force later on in the question, but what I want to notice is here's friction. And how big is friction going to be when it's static? It's going to be 0.3 times, I don't know the normal force. Oh, but look, another force the same size as the normal force. Which one? Liam, look up. I don't know the normal force. Oh, but look. You were overcomplicating it. What's the maximum friction can be? Can you crunch that? 0.3 times 5 times 9.8. Going to be 14 point something, I think. 14.7, even all the sig figs? Okay. So, Liam, I'm going to ask you a couple of questions. I'm going to phrase them differently, but I want the same answer. How hard do I need to pull before this will start to accelerate? How big is the maximum force of friction? Okay. How hard am I pulling in B? Is this object going to accelerate? So I can answer B. It says find the acceleration. A is 0. How big is friction? Not 14.7. If A is 0, if I'm pulling with 10, how big must static friction be? What if I pulled with 12? How big would friction be? What's the tipping point? Anything above 14.700000000. Let's just say 14.7, bang on. How hard are we pulling in C? Is it going to accelerate? And now I'm going to calculate friction, but with this one. So now in part C, it is going to accelerate. First thing I'm going to say is friction is going to be kinetic times the normal force. It's going to be 0.25 times mg. It's going to be a little smaller. And this friction will be steady while it's sliding. How big? Oh, you're still writing? Okay. Friction equals mu k, that's kinetic, right there, times the normal force. So 0.25 times mg. Luke, what'd you get? 12.25? Okay. So now we can find the acceleration. Liam, coming back to you. Who would be winning? Oh, you're still writing. I'm sorry. I apologize. I'm going a little fast. Take your time. Okay. Part C says the object is pulled with 20 newtons. Find the force of friction. Now, we did. We said it's sliding, so it's going to be this coefficient of friction. And the acceleration. How are we going to find the acceleration? Who's winning? Losing? Equals? Yeah, we're going to go F applied minus friction equals MA. Liam, get the A by itself. Divide by M. So now we can say it's going to accelerate at 20 minus 12.25 divided by, that's a 20, Mr. Dueck, divided by 5. That's not a 10, that's a 20. That looks terribly messy, Mr. Dueck. It's gonna be small. Oh, is that what I thought I heard 20.15. I was going, I don't think so. Is it 1.55 meters per second squared? So Liam, so Evan, so Julia, I've talked about how technically there's always two types of coefficients of friction, but if you see one in the question, you can use it for both. I'm not going to distinguish between the two. I got a cool video, but first I want to let you know the homework. What did I assign my block D's? It's going to be the same. You can cross out 7 and 8. By the way, 4, 5, and 6 are so easy that they're tough. I made a QR code solution key. If you scan that with your phone, that'll take you to a YouTube solution for 4, 5, and 6. I gave you these same questions last year. I'm curious to see if you've internalized it better and can actually wrap your brain without having the struggle. But I included the same QR code. So you can cross out 7 and 8. And then on the next page, you can cross out 11, cross out 13, 15, and 16. So do me a favor, let me go back to you folks, block G. Can you tell me which questions I said to cross out? I said you could cross out 7 and 8, right? 11, 13, because I'll put, and 16? Okay. Let me hit pause for a second.